Hey guys, what's up? Eddie Alhole here with KissAnalog.com. Today what I want to do is do a quick video on how to set up your FFT and how you can trust measurements. We'll do a little calibration. I'm going to show you this. We're going to bring the camera, do this quickly, and at the end of the video I'm going to do a little more discussion about this, okay? But let's just come over here and set it up, because I understand some people don't feel comfortable or don't trust the measurements, and it does take a little bit more setup with an FFT to get it right. So let's come over here. I'm going to show you how to do it. Okay, so let's just first start off with our setup, okay? So I've got the generator on this lead right here and this guy, and it's tied to these two guys, which go to this multimeter so we can see what the voltage reading is. And then we have an oscilloscope probe going to the scope over here that I'll show you. And so we just got everything connected together here. Alright, so let's just look at our scope setup. And you can see this nice signal. It's got, you know, what? We got 1, 2, 3, 4, 5, 6, 7 cycles roughly. And they're pretty much filling the screen. Looks pretty great. It's 500 microseconds per division. Up here it says 1 kilohertz. And right here we got 1 volt. And that's because on the measurement menu, on source channel 1, I went to type and we chose RMS, okay? And it said probe is set for time 1x because the scope probe itself is set for 1x. No bandwidth limit, AC couple, 1 mega ohm impedance, and no invert, and we're on units or volts. Okay, let's go back to page 1. 500 millivolts per division, so that's our normal time base where we can see amplitude and frequency. Okay, that's great when you're looking at a single frequency. Now let me scroll over here and I'll zoom in a little bit. Alright, then we come over here to the multimeter. It shows 1 volt and 1 kilohertz. So we're all in agreement. Everything looks great. Okay, now let's do the FFT. Okay, let's just zoom out right there. Okay, so let's go to Math and FFT. And I think we're already set there, FFT. Okay, we're on page 1 of 3. And our frequencies are here. So I'm just going to say, okay, you know, here's our source, channel 1. That's what we're coming into, so that's great. That's chosen. And then we have center, frequency, you know, where we want to put right in the middle of the scope. And then we have Hertz per division, how many cycles per each division. So on this window, the other thing is this math menu. Rectangle, Blackman, Hanning, Hamming, and flat top. Those are all basically mathematical filters, the way they do the FFT. And for the best amplitude and also good frequency is Hanning or Blackman. We'll just choose Hanning, okay? So now let's go to page 2, and you can set the units is VRMS, or we go decibels, but we'll go to RMS right now. Normally I use decibels, but let's just do that. Reference level, that's where it's setting here. Scale, how many volts per division? Right now it's 2 millivolts per division. And then display exclusive. So we go full screen, which will show the frequency and this, or split screen. So it's nice to see this where make sure but we know our waveform's good, so I think it's okay. We can ignore that. We're not going to change the volt scales right now, so you just don't want this to blow off the scale, because then it's going to clip and you're going to see distortions down here. You just want a nice clean waveform up here in so many cycles. And that the cycle number is what I'm telling you is what we're going to end up making the difference here. But let's just go to exclusive for now. And then let's go to page 3. There's a max hold, and here's this max points. You want to make sure you're maxed out. And this one's 16,384, not a million. If you have a million with the X-E, do that. And then operations, FFT of course. So, okay, let's go to auto set. Now when I push auto set, it's kind of like this button over here, watch what happens. It's going to put the waveform right in the middle, and it's going to kind of use up the vertical display, you know, with the peak, the amplitude, and so on. So, okay, now it's right in the center of the screen. And look at this, the math for this, when you do the math, by the way, I've already had it set up, but when you go measure, source, and you go down here to math, and then type, there's only one thing option you have. Everything else grayed out, it's maximum. So that's selected. So that's fine. That's what we want. So you can see 1 volt here, and it's 997 millivolts, point, you know, some fraction. And so pretty close to 1 millivolt. Now that has to do with the resolution, the math, the Blackman, all that kind of stuff, but right now that's not too bad. Alright, so how do we improve that? Well, here, let's go to page... Here, let's go back to math, and let's go to the page where we can set up the center, frequency, and the hertz. So, if we want, right now we got 800 hertz in the center, and that should have been 1 kilohertz. It's 1K, but it kind of thought 800 must be the closest because it goes to 1200 to 400. And the reason why, it just doesn't have the resolution to find smaller points than that. We can go to this thing here and try to get a small, see, it goes to 20 and then 200. So we really can't get less than 20. Problem is we're at 500 microseconds. We only have about 7 waveforms, and with all this deep memory and stuff going on, you need more cycles. So if I just go back here, I'll just show you I'll turn off the math real fast. See these cycles here? Really, we need more. So let's say we go to 2 milliseconds, okay? And let me go back to math. Alright, now let's see the center. Now we're at 0. If I rotate it, it goes 100, 200, 3. So now it's every 100 hertz. So we have 100 hertz resolution. That's not bad. But we can get better than 100, but 100 is not too bad. Now we can get 1,000 in the middle, and Hertz per division's 5K. That's 5,000 hertz per. Let's get less than that. Well, that's as small as we can go. So 5, 10, 15, 20, 25 kilohertz out here. And then, you know, 0 kilohertz is like, we're at 1, so it's right there. So we're wasting this part of our screen. So if I put the center at 5K, he's moved over, we got some more, but you know, we really want this to be less. Well, to do that, you have to have even more cycles. You have to have more resolution. So we're at 2 milliseconds per division. Okay, there's 10, there's 20. Now 20 milliseconds per division, let's see what we can do. Now look, this 500 hertz per division, that's a lot better. It's like 10x better. So we got 10 times more time, and we got 10 times better resolution here. So now, that's still as good as we can get, but now look, we can go to 1K. That's great. Now I can go 1K right here, and 2, 3, 4, 5K in the center, and out to 10K. So 20 milliseconds, you know, we're looking pretty good. 995.9. Okay, I'm wondering if we can do better than that. Let's go up again. Let's go to 200, another 10x factor. Now we're in roll mode. You got to turn off roll mode, okay? And now we got a lot of time, so it takes a moment for it to capture this. There we go. Okay, now it's off the screen because we got to reset this. But now look, now we're all the way down to 100 hertz. So we got lots of resolution. There's 50 hertz. We got all the way down to 50 hertz resolution. But now if I go up, I can only go as far as 500 hertz. What I really want to do is I want to have 5K here, 10K here. So I want to go 1, 2, 3, 4, 5, all the way up to 10. So I kind of like the way I had it before, and I can't get 1K. So that's, if I drop down to even 100 milliseconds, I can get 1K again. Okay, now I can go to 1K, And if I wanted to, I could go all the way down to 100 Hertz. So now I'm capturing plenty of points. Now this is 1K in the middle, so I want to go back to 5K. This button, if you move it quick, it speeds through things, so you got to be careful because you kind of end up going back and forth. So now we got 5K and 1K resolution. And look, this is 987, so it's a little bit better than I think we had before. So that's looking pretty darn good now. So there you go. That's how you set up the time base so that you can get good accuracy. Now look how narrow that is. That's what you want. You want a narrow spike. You don't want this TP, okay? You want a very narrow spike. Because what if you had another frequency at 1.1K? Well, this guy's so narrow that you could actually see that. Okay, now look what I've done is I've changed our frequency to 1.2K. So now it's just slightly off that 1K, and the amplitudes, I've dropped it down a little bit. It's just at about 788 millivolts, and right here it says 800 on the multimeter, so we're pretty darn close. Okay, now let's go back to the FFT. Oh, but before that we got to collect a bunch of cycles, right? 100 milliseconds. So let's go back to 100 milliseconds. We got to turn off the roll. But look at all those. That's a lot of data we're gathering, and that we can do that with the deep memory. So what we want to do is, now by the way, if I haven't shown you yet, go to acquire, make sure you got maximum depth 14 million, okay? But now what we want to do is go to FFT again. And let's see, hopefully we're still set up. Okay, we are. Now, see, 1 kilohertz is that last line. See how we're just off that? And we're right at 798. Real close to the 800. So, we're very close to the 800. We're all kind of lining up, right? So, I think we can count on that. And the frequency is right at, you can see it's just right off. I could get the cursor on there, but you can see it's just off of the 1 kilohertz. So, that's great. Now let's go ahead and throw that 1 kilohertz signal back up there. Alright, so now look at that. We got one at 1 kilohertz, one at 1.2. And see, they're just these very thin lines, so you can actually capture both signals, and you can see the amplitude of each one. Now the multimeter is combining those two things and giving us this reading here. And it's saying 1.09 kilohertz, so it doesn't really know what to think of this reading. But yeah, so now with this, we can see our max is at 984 up here, and we could use our measurements to go to each one of these peaks. But I just want to show you how you can see it on the screen, and you can read from the display like what the measurements are. If you use the cursors, you want to come down here to Y, and you want to go to source as math, and then we're in manual mode right now. You can go to track, you can go to different kinds of things, but from this, whoops, okay, so we got to go down here Y again. Thought I had that selected. Okay, now I can come up here with the cursor and put it right there at the top of that guy. And over here I can read off my 800 millivolts. And then I can move it up here. Yeah, it's 996, I guess. It looks like the amplitudes and everything are looking great. Okay, but let's go ahead and put that pilot at 4.5K. Now that pilot's only 1% of 1 volt, so what is that? That's 10 millivolts. Let's set that up. Okay, let's just zoom in on the screen a little bit. Alright, so what we need to do is come over to math and FFT mode, and we need to go down to our reference level and our scale. See, we're 200 millivolts per division. We're going to be looking for a 10 millivolt signal. All right, so let's go scale and change that to 5 millivolts per division. Now, there's our waveforms just taken right off the screen. But we also wanted to see the bottom of the waveform here, so let's move it up. I think we want to be at about, so if we're at 5 millivolts per division, 5, 10, 15, 20, 25, 30, say 35 millivolts. So if I move this quick, it moves it real fast. Okay, and there's 35 millivolts. So you can see a little bit of noise down here. This is 5 millivolts and that's 10. I'm going to turn off the cursors for a moment. So you see a little bit of noise from the generator, I guess. Okay, I'm going to take this second waveform and drop it down 10 millivolts and move it over to 4.5K. Alright, so I've turned off the 1 volt signal and all I have is the 10 millivolt signal right there, 10 millivolts at 4.5K. Now the signal is so small that the frequency generator is having a hard time picking up the frequency. But I know this is 4K and 5K and that's right in the middle, so my generator says 4.5K, so I think I can start believing this. I could use my cursors to, if I didn't know what that was, I could use my cursors to come over there and identify that. But now let's just go look at, and right here, saying about 10 millivolts. Okay, let's go look at the scope. Let's turn off the math. Now look at this signal. So if I spread this out, yeah, about 10.96. It looks like my generator at that low amplitude has a little bit of wobble, so it's not too great. So let's go back to 100 milliseconds per division and take it off roll mode and go back to FFT. Okay, so there we are. Okay, we're back in FFT window. Okay, now I'm going to turn on our signal again, our 1 kilohertz signal. We're back at our window and I've got the 1 volt signal here and the 10 millivolt pilot signal here, the 1% signal at 4.5K. And you can see a little bit of spiky stuff down here, just some high frequency stuff, but looks pretty good. Now I went ahead and put another signal on there at 4.6 kilohertz and see the resolution. And there's that little pesky signal popping up there. And it looks like it's about 20, it's in between 20 and 25 millivolts, is 22.5, 23 millivolts high. Well, let's turn off these other signals and see if that's what we read. Alright, I turned them off and all I see is about 18 millivolts. It looks a little bit low. I think this meter is 4.6K, 4.7, 4.5. I think the reading might actually be even a little bit low and this meter's having a hard time catching on. Now this guy has a pretty high bandwidth. Let's go to our Keithley because I want to do a distortion measurement as well. Alright, so it's 23.4 millivolts, so that seems believable. Okay, what I'm going to do is, let's go back down here. You know what I want to do? Let's see what that Keithley distortion meter reads when we set this up. Alright, we got our 1% back. Let's get our other 1 volt signal, our prime signal. Takes a moment. Okay, there it is. Now let's go up to the Keithley to see if we get a 1% distortion. Now this is not a harmonic, so we have to do something a little bit different. Here, let's go up here. Alright guys, so this guy here, I'm reading 1.02 volts, which is pretty close to our 1%. Now if I go to THD, I push this, THD, okay, there's 1.1% distortion. That's pretty close actually. Let's go to measurement. Now we're actually measuring THD plus N, plus noise. If I turn that off, if I go to THD alone, look at that, it's 0.07. So
I need that noise because it's not a harmonic. So it thinks it's noise, which it is because it's not a harmonic. So go back to measure and THD plus N. And we get our 1%. Almost 1.1, but that's pretty good. Alright, so we've set up with known signals using generators so we know what the value is, and I think we can trust the display. I mean, it might be off 1 or 2%, but that's pretty darn good when you can see multiple frequencies, a whole lot better than you can on an oscilloscope. Okay, you want to see what this looks like on an oscilloscope? With the normal time base instead of frequency base down here. Let's see what it looks like with time. Let's turn off our math. Okay, there we go. Now let's zoom out. Well, we can see our 1 kilohertz, and we can see it wobbling a little bit, so you might guess that there's another frequency in there. Or is that noise? It's kind of hard to tell. Sometimes when you zoom out, you can look for low frequency ripple, but it doesn't look like a low frequency ripple. Now we know it's actually a 4.5 kilohertz, ripple, a higher frequency, and so it's adding and subtracting as it moves along, and it's giving this kind of gyration, that kind of weird, it's kind of giving that weird modulation. So that's where the spectrum, that's where the FFT really comes in handy, because you can go to FFT and see what the heck's going on here. So imagine if this was a ripple on the output of a switching power supply. You might see this sawtooth waveform and you think, okay, okay, I see the frequency. But if you go to the FFT, you might see that there's multiple frequencies in that. Most likely you would. Alright guys, so I hope that's starting to make a little more sense and you think you can, feel more comfortable trying your own scope and seeing if you can take some readings. Now, this was an audio example where you're looking at audio distortion. Hey, by the way, if you haven't subscribed, please do so and give the video the old thumbs up. That really helps a lot, guys. So just go ahead and smash that like button, the old thumbs up button. And thanks, Patrons. Appreciate your support. And anybody supporting on the PayPal link below, it's really appreciated. Okay, so let's just talk about this a little bit. The more memory you have, when you have these FFTs capable of, like, say, 16,000, like on this 1202X, now the X-E go up to 1 million points. Like this GW Instek can go up to 1 million points. That's becoming more common in the newer release scopes. So that's what you want to look for, is 1 million points. With that, you can refine the resolution bandwidth. When you get enough points that you can have a bandwidth where those peaks, they get really tall, like what we saw here, tall and skinny. So if you have another frequency right next to it, you can get all these other frequencies. Now if you're looking at harmonics, they're spaced wider apart, but you could have noise and frequencies right next to each other. So it's great to be able to see those individual frequencies versus having that TP looking thing, that big wide looking spike that comes up like this, and down here it might be a whole 1 kilohertz wide at the bottom maybe. And so if you have a 1 kilohertz and a 2 kilohertz, they're kind of muddled together. What are some of the other things you could use this for? Well, if you have a switching power supply, say switching a 100 kilohertz, you'll see a spike at 100 kilohertz, right? But you might see some other spikes out there at, well, the harmonics, or you might see something out there, say 20 meg or 30 meg. You might see these little spikes out there, and that gives you an idea of what the EMI is going to look like. Because those sharp edges, they'll give you high frequency, distortions. And so you can see that using your FFT. In scope mode, where you're looking at the time versus voltage in a normal scope, you can see some high frequency riding on top of your waveform, or maybe even see low frequencies for that matter.
you know, you might be switching 100 kilohertz, but because of not having enough bulk capacitance or maybe something like that, you might see this low frequency, you know, 400 hertz or 40 hertz thing going on. And with this, you'll see a spike down there. You know, you have to kind of search around a little bit and refine your bandwidth to get the best picture. But I hope, you know, this example helped you there. Give me some questions, give me comments, ideas that maybe I can show you some other measurements so that we can all feel more comfortable using FFT and confident that, you know, those amplitudes are correct, that we have the right settings on our scope. Okay? Alright guys, hey, thanks for watching. We'll see you next time.